So these are the contents for today. I would be taking you through what is SAE, a brief introduction on SAE, and what exactly it means by autonomous driving, and what are the levels that has been defined by SAE for the autonomous driving. And as I told, some example of this autonomous control systems, and also example of a model-based autonomous system. And last, we'll be taking some questions and answers. So first, to start with SAE, what is SAE? Okay, so as the abbreviation goes, it's known as Society of Automotive Engineers. It's a US-based globally active professional association. So back in 1900, there were dozens of automotive manufacturers worldwide, and these OEMs and the suppliers joined the trade groups to promote their business. They saw a need of a platform to solve the common technical design problems and also developing engineering standards. Yeah, it was start of the market, and also the defining the standards were very much important that time. And also these engineers in the automotive business expressed a desire to have a free exchange of ideas to expand their technical knowledge base. So that was the time when these two magazine publishers, one is Peter Hill from Horseless Age, and Horace Switzerland, he is from the automobile. So they were the advocates of the concept for the SAE. So this was founded in 1905, and currently in 2020 they have globally 138,000 members. They are providing industry standards, the memberships, conferences, and they arrange conferences on different topics, new topics, and the standards they define. So mostly they emphasize on transport industries such as aerospace and automotive. So they design the standards for new standards and also maintain the old standards. They basically modify the existing standards also. Works that they have done is very few, but there are many which you can go through by going to the source that I have mentioned here. So one is horsepower rating. So I hope all of you are aware of what is horsepower. It's a unit of measurement of power, or the rate at which the work is done. So one mechanical horsepower lifts 550 pounds or 250 kgs by 1 foot in 1 second. So SAE provided, so without taking care of the transmission losses of an engine, taking into account only the engine accessory emissions and exhaust drags, they defined what are the horsepowers of an engine. Next are some of the industry standards for the aerospace field or domain also they have. And the last one that I have mentioned here is SAE J3016. Here they have defined 6 levels of automation for the vehicles. And so all the OEMs and the suppliers should be adhered to the rules and regulations defined by them in order to publish or put any autonomous vehicle on the market. So next comes, I hope that gave you brief information about what is SAE and what they are basically does, and what is my reference for today's. Next is, what is autonomous driving? Yeah, let's first take a look now on the basics of autonomous driving. So a self-driving car or autonomous vehicle, as it goes by, what it does is it senses its environments, and then sensing the environment, it plans for a safe maneuver, and then this plan further gets actuated by the actuators that is in the vehicle. So first, to sense the environment, we have a radar, lidar, camera. So as you know, radar uses the electromagnetic waves in the radar or microwave frequency. Lidars uses the light pulses. Sonar uses the sound pulses. Camera, as you all know, GPS, odometry, and inertial sensors, basically to give the idea on your ego's movement and ego's position. Ego means the vehicle which I am driving, and radar, lidar, camera, sonar, these are to detect the traffic around the environment which is there around the ego. So now when I will be saying ego, that you have to understand the vehicle that I am driving, that is having this autonomous driving feature. So you use the radar, lidar, and camera, sonar, this kind of sensing hardwares to detect the environment. So there could be different environmental factor like the traffic signals, and also the static environment means if there is a curved stone or something, those kind of things. So this can be detected by this sensing hardwares. And then finally, this information will be given to a model which will plan the safe maneuvers of your ego in the defined environment. And lastly, this model will give me certain informations like at which acceleration rate my ego needs to drive, at what steering angle is required to move my ego in a lateral direction. certain kind of things, and then that information will be fed to my actuator lastly. So actuator is nothing but the existing things like brakes, steerings, and the powertrain model for the engine torque requests. So this is the complete closed loop things that you see here, from sensing to planning and to actuating based on the environment around my ego vehicle. So let's understand why is it so important. So I've just put an example here from SlideShare is the source. So if you see a human is driving a vehicle at a speed of 60 miles per hour, and if he feels there is a need of braking, it takes around 2 seconds for him to identify a situation that where a braking is required, and then he does a manual braking. So it takes almost 300 feet to come from when you realize the situation and from when you come to complete standstill, and it increases drastically when the speed is more. So around 90 miles per hour speed when you drive, it takes almost 600 feet to stop the vehicle by the time when you realize, okay, a braking is required. Comparatively, if it is done by a CPU, it takes hardly 300 milliseconds to understand the situation, to plan the ego movement, and then apply the brake. So if you see here in the at the same ego speed 90 mile per hour, it takes 300 milliseconds to detect and start the braking process, and it takes another around 300 meter to make your ego to a complete standstill situation. If I discuss some of the advantages of the autonomous driving, so reduction in accidents. So this example would have given you idea why I have written this point. Optimal speed. So in certain highway situations, when the highway speed is suppose if you are not supposed to go beyond 80 kph or 90 kph, in certain situations we see that we do not always see the odometer of the vehicle to see what speed I am driving. If I have a free road, I will simply drive. But in countries, in developed countries like US or UK, this is everywhere there are cameras which will detect you if you're overspeeding or something. So if this kind of control models are there, that they can maintain optimal speed on the highway situations. So that means efficient use of highways when every vehicle is having a safe distance with each other and they are driving with keeping all the laws in mind. So next is maximum utilization of parking space. So when manually you are parking, you might have faced there are certain situations where in tight parking situation it becomes very difficult and time consuming also to put your vehicle in a designated spot. So if it is done by a control model which will be taking care of inches, even there are few inches also is gap is there, that will be also taken into consideration when you are parking your vehicle. So these are the few advantages I have written it here. So obviously this is having some disadvantages also, especially the weather conditions to affect the environment sensing. In certain conditions, suppose if it is raining heavily or if it is snowing, so in those kind of situations, when your camera cannot see what is ahead, the sensing hardware basically, or your radar is malfunctioning, then it becomes difficult to carry on with the autonomous driving. Chances of hacking in this ecosystem of autonomous driving, all the autonomous driving vehicles needs to talk to each other. So suppose I am going ahead in a particular road and I see there is a road blockage. So if this information I can pass to another vehicle coming behind me, then that person can avoid the taking the same route. So in this kind of communication mechanism, obviously there are few more, but this is one prominent example I could think of right now. So in this kind of situation, when this communication is happening, there are chances where third party people can do a hacking and they can manipulate the data that is being sent from one autonomous vehicle to another. So obviously there are measures now in terms of cyber security, but that is also under development currently. So not all use cases are ready. So what does this mean? So suppose when I am making a vehicle ready for autonomous driving on highway situations, in certain countries or in certain conditions, suppose the markings, the road markings and all are not correctly there, then what are the exceptions that this vehicle or these control models need to handle? Those are not all are known actually at this moment. So use cases are still being built, and those OEMs are driving millions of kilometers to understand what are the use cases that may arise when they are putting these vehicles on the market and they are ready for to be used by normal users like us. These are the few challenges that is still there in the autonomous driving ecosystem. Basically, if you see here, the vehicle can move in a 2D plane, so it has a movement that is possible in the X direction and also in the Y direction. So in the vehicle coordinate system, when you go ahead, it is in positive X direction. When you go backward side, it is negative X direction. When you drive left, it is positive Y, unlike the normal Cartesian coordinate system. And in the right side, if you drive, it is in the minus Y direction. And theta is the angle of in the direction of my ego. So at a particular time, if the reference point is the rear center of the ego, then x, y, and theta can be considered as the vehicle position at a certain time. So how do you control this x direction movement? Using throttle and the brake. So throttle to accelerate in the x direction and brake to stop it in the x direction, and y to steer. So positive y to steer in the left direction, positive negative y in negative steering to drive in the negative y direction. So what is the motive of this autonomous control models are? Either they can automate the movement of your ego in the longitudinal direction or in the lateral direction or in both the directions, depending upon which levels of autonomous driving they belong to. Okay, so now next I come to what are the SAE levels for the autonomous driving. This has been standardized SAE J3016. So starting with level 0, that means no automation. So most of the vehicles that you see on Indian roads are on level 0, where all the longitudinal movement and the lateral movement has to be taken care by the driver itself. So no automation there. Next comes level 1, which is known as driver assistance. So here the assistance to the driver will be provided either in longitudinal direction or in lateral direction. But the driver has to be always attentive to the situation, that is the environment that is around him. And at any point of time, these control systems can fail and or give warning to the driver that, okay, I'm not capable of handling the situation right now. So you have to immediately take control of the driving now. So that is where the system monitors always the driver has to be attentive to the to the situation ahead of him. So some of the prominent examples of a driver assistance system could be adaptive cruise control, emergency braking assist. So I will be taking you through this control models one by one after I have that in later part of my presentation. Next is the level 2, the partial automation. So here, unlike in level 1, here the longitudinal and the lateral can be controlled at the same time, but the use case has to be defined. So the system has to know where it is driving. So if you are driving in a highway situation, then the control model can take care of longitudinal and lateral motion at the same time. But if you take a diversion to the city road, then the control model won't be again capable of taking care of this motion. Maybe that time it will be capable of taking care only about the longitudinal using the adaptive cruise control. But in this situation also, the driver always needs to be attentive to the situation, and at any point of time it will zero latency will be given to the driver to take care of the driving. Next comes the level 3, which is known as conditional automation. So what conditional automation does is, here also it is the same approach. The longitudinal control and the lateral control can be taken care at the same time, but here the system is capable of identifying its own limitation. So suppose when you are driving, all of a sudden it starts raining heavily. So that time the system will still try to adapt to the situation, but if the camera is completely blocked, suppose it is not able to see what is happening ahead of it, it will give some time to the driver to take care of the driving again. So it is not like immediately the warning will be given and the driver needs to handle the situation. There will be certain time given, depending upon the situation again, that okay, so I am not capable of taking care of the automated driving at this moment, you please take care of the driving. So this is level 3 of automation. And whatever autonomous system that you see on the market now, be it the Tesla autopilot or the Audi e-pilot, anything, all falls under the level 2 plus and level 3 starting of automation. Next one is the level 4, which is known as high automation. So it's the same deal goes here also. The steering, acceleration, and braking can be taken care by the control model by itself. Unlike level 3, it is capable of monitor the road conditions. So suppose when you are driving at a highway, you are cruising at a highway, and suppose there is a road blockage is there. There is a marking that, okay, a road blockage ahead. So what this kind of control model is capable of doing is, they can divert their lane and they can come to a next lane which is free of any obstacles, and then can continue the driving. No driver intervention required whatsoever. Yeah, but still certain conditions like traffic, identifying traffic jams and all these kind of things, or major obstacles like a vehicle breakdown. If a vehicle breakdown happens, and these kind of situations are not able, this kind of control model is not able to detect and react accordingly. Level 5 is known as full automation. So here no actuator is present for the driver. So that means no steering wheel, no brake, no accelerator, no gear changing gear shift pedals are present. You just need to be into the car. You just need to tell where you want to go. The vehicle will take you through. Whatever condition, whatever situation may arise, even if it is raining, it is snowing, the traffic signs are not recognizable, does not, it should not matter for the control model, and that is where everyone is heading towards the automotive world. I would be taking you through some of the examples of the control systems that is present in modern day cars. So I have segregated them based on the detection range. So if you see here, long range radar, which is capable of identifying an object and giving its dynamics from a range of 200 to 250 meters. There is a LiDAR 200 to 230 meters. We have short range radars 80 to 120 meters, multifunctional cameras typically 120 meters, and ultrasonic sensors around 150 centimeters. From this detection range, you can understand that long range radars and LiDARs are capable of handling high speed applications, something like cruising, emergency braking, these kind of situations. The short range radars are capable of taking care of mid-speed applications when your vehicle is moving at a speed of suppose 70 to 80 kph. Ultrasonic sensors are having very low detection range. So these can take care of applications where your vehicle moves at a very low speed around 20 kph maximum. So keeping all these detection mechanisms into mind, you can see here some of the features that I have noted down here. So adaptive cruise control. Uh, okay, so camera, I will explain why camera is generic for all this. So adaptive cruise control can be taken care by the long range radar or the LiDAR. Emergency braking, pedestrian detection, and collision avoidance, this kind of things, this kind of features also can be taken care by the radar and LiDAR. The lane departure warning and the traffic sign recognition can be needs to be done by the camera. The camera needs to see what is the traffic sign ahead of me and then accordingly parameterize the control model which is running the vehicle. And lane departure warning, I would come to this in the next slide. We have mid-range radars that takes care of the blind spot detection. So suppose there are certain conditions in highway situations, you want to overtake a car and you want to do a lane switch. But if a vehicle is somewhere here and your ORVM you cannot see that through your ORVM, then this short-range radars will come into picture. They will continuously monitor the objects at your blind spot, and you will notify whenever you give an indicator and try to do a lane switching that it is not safe for lane switching. So we have rear collision warning systems, cross traffic alerts. So basically in urban situations when there are too many cross roads where there could be pedestrians or bicycles coming from this direction, which cannot be always seen by the driver when suppose you are driving at a speed of 60, 70 kph. So this kind of features can be taken care by the mid-range radar. Ultrasonic sensors, as I told, the detection range is hardly 150 centimeter, 15 meters. So these are mostly impactful for the parking assist and also backup assist where you are moving at a speed of 10 or 15 kph. And cameras for the surround view again. So if you have seen the modern day high cost cars, they have the surround view where they stitch the information from multiple cameras. So something from this camera, something from this camera, from the front viewing camera and from the rear viewing camera, all these bits and pieces can be taken and stitched together using the digital signal processing, image processing, and then that can be presented on your monitor to give a top view where your vehicle is driving. So why cameras are so mandatory nowadays is in case of radar, suppose if you take radar into picture, there are road boundaries or road barriers or guardrails, or if your frictional coefficient of the road is too less, then what happens is there will be too many false echoes coming back from this kind of objects, and it will form a ghost object, or what I can say is a false negative that we call in our industry. So even if the object is not present there, still radar will form that object with multiple other echoes that is getting reflected from some other road static conditions. So camera comes handy in those kind of situation to detect any false negative, whether the object is at all present there or not. So this is why camera is so much mandatory nowadays for the systems that takes care of adaptive cruise control or emergency braking to avoid false braking or false accelerations. Okay, so here I have some examples of the autonomous control models which you can see nowadays in the cars. So starting with active parking assist, it belongs to L1 autonomous level because at a particular time only lateral movement of your vehicle is considered here. So what it will do is you need to indicate when you are driving, suppose you need to indicate which side you want to park, whether in the right side or in the left side. And your ultrasonic sensors will throw the sound pulses and try to detect what is the parking slots that are available. So suppose if you want to do a cross parking, it will check if the parking space width is more than your vehicle width plus whatever space you need to open the doors, something around 50 centimeter in the both direction. The calculation will be done internally by the control model after the ultrasonic sensor provides this information. And then if the parking spot is suited for your vehicle, then it will tell you, okay, a parking spot is available, please stop. So once you stop the vehicle by putting brake, it will ask you to engage a reverse gear. So as soon as you engage a reverse gear and put little bit of throttle, then your vehicle will start moving backwards. And to place the vehicle in the correct position, what will happen is the steering will be automatically taken care by the control model. So it will rotate your steering in such a way, keeping the the acceleration you are putting into picture, it will automatically do the steering movement, and it will place your vehicle in the particular place. Same goes for the parallel parking slot also. So since it is only, since the gear change and also the throttle positions are taken care, throttle positions I mean for the acceleration, it is taken care by the driver. So that means the longitudinal movement is taken care by the driver. Only steering is being automated by the control model. Hence we are calling it as a L1 autonomous system. So next comes the adaptive cruise control. So this is also a L1 autonomous system where suppose at a highway situation you want to drive with a constant speed of 80 kph. So you set the set speed as 80 kph and you just relax, just keeping in mind, okay, nothing is coming ahead of me or no one is doing a cross movement. If cross movement or something is happening, that also this control model is capable of taking care. So what will happen is, if you are driving at a speed of 80 kph and suppose the vehicle ahead of you is driving at a speed of 40 kph, then automatically the speed will be adapted of your ego speed of your ego, it will be adapted automatically. So your ego will now drive at a speed of 40 kph. Now suppose you want to overtake this vehicle, slow moving vehicle. So what you will do is, you will give an indicator to the fast moving lane side, and then you will do a little bit steering. When you, at the moment you do a little bit of steering and put an indicator, the control model will understand this guy wants to overtake. So what it will do is, it will put more throttle so that you can overtake this vehicle, and then again it will drive at a speed, the set speed that you set 80 kph, until another vehicle comes, slow moving vehicle comes in front of you in your designated lane. So here also the steering and the indicating of the lane changing is being taken care by the driver. Only in the longitudinal direction the movement of the vehicle is being taken care to slow down or to accelerate. So that is why it is also L1 autonomous. So in this function, as you saw, it's the steering the steering automation, the lateral movement automation. Here it is the longitudinal motion automation. Lane departure warning or lane keep assistance systems, that falls under L2 autonomous systems. Like, it's very basic of L2 autonomous system. So what happens is, you have a camera mounted at the back of IRVM, and there it constantly monitors the lanes at which you are driving. So at any point of time, if the road is suppose curving, or you without giving an indicator you are changing the lane, it will give a warning that you are going beyond the designated lane. And lane keep assistance system, what it does is, it does not give it gives a warning, and after that it rotates the steering automatically, so that you are brought back to the designated lane one more time. Now to control the lateral acceleration, so suppose if there is a curvy situation, you are going out of the designated lane, and so to bring you back to the designated lane, if the lateral acceleration of the vehicle, keeping the vehicle dynamics in mind, so that you do not skid or something, if that is calculated that you are at a higher speed, then automatically braking will be done by this model, so that you slow down a little and you steer back properly in the designated lanes. So the similarly, what you do in a curvy road is, you slow down and then do the steering. So this is automatically being taken care by this control model. So since only braking it does to control the lateral acceleration and also the steering to bring you back to the designated lanes, that's why we are calling it as a L2 autonomous system, where lateral movement and also longitudinal movement in terms of only braking can be taken care, and that is why I called it a basic L2 autonomous system. Next one is a traffic jam assist. So here we have coupled the lane keep assistance systems and the ACC system. So from the previous slide, if you remember the adaptive cruise control system, so these two are merged together to create a traffic jam assist system. So what will happen is, when the ACC can become handy when you are driving and the vehicle ahead of you stops completely, and then as soon as it starts moving, your ego also starts moving into that direction. And also in this process, if any point of time the driver does a steering or something without, again the same thing, without indicating or something, then it will be automatically brought back to the designated lane again. So the longitudinal control is being taken care by ACC, and the lateral control is being taken care by the this LDW or LCAS system. So that is why we call it a L2 autonomous system. So these are some examples which you can see present in normal day in modern cars. So if you see in Tesla, this traffic jam assist is present there, and also the adaptive. So this traffic jam assist anyway is having the ACC and lane keep assist embedded. So that is why Tesla calls it as an autopilot, and where they have this L2 autonomous, the advanced L2 autonomous system achieved from their side. There are exceptions. As I told you, I'll give an example here from Tesla only. So if you remember a few days back, there was a news that one Tesla has rammed behind a truck. So the situation was there, the truck's color was white and it was completely merging with the sky color, and the camera was not capable of classifying it as a truck. So the autonomous system could not take care of the situation, and it directly went and rammed the truck. So this is where this point comes into picture. All the use cases are not known. If you remember, I mentioned this at start of my presentation. So these are the use cases, certain use cases where wrong classification, false negatives, this kind of situation is harmful for the autonomous control systems. And also when this kind of situation is on road, you never know the other driver on the road what kind of manipulation of the environment that person can do. So that is why it is still risky. Next, I have an example of control of a model based autonomous system. So I'll just give you a functionality that I have taken into account. So my ego vehicle drives at a particular speed on the highway, and I have a sensor mounted at front grille of my vehicle, and it is capable of detecting an object that is at a maximum range of 50 meter. And this sensor will provide me the information such as the relative velocity of the object and also the distance to the object. And once I have this information, what I would do is I will check what is the speed at which my traffic is driving ahead of me, and I will adapt to that speed. So this is the control model written in C code. So first I am checking if the object is detected by the radar or not, this 50-meter radar or not. So if it is detected, if it is not detected, suppose, then what I will do is I will make a constant throttle position of 20% to keep my vehicle moving at a steady speed. If the object is detected, then what I will do is I will calculate what is the target acceleration. So I anyway have the relative velocity from the radar, and I have a time to react. So a T hard coded as 2.5 seconds. So that means if my ego is moving at a speed of u kph and the traffic is moving at a speed of v kph, then how much time I need to make my ego speed shift from u to v. So for that, I have kept a time constant of 2.5 seconds in the example that I would be showing you now. And then with that information, I'm calculating what is the acceleration required from my ego vehicle. So I have my inertial sensor from my ego that will tell me what is the acceleration, the current acceleration of my ego vehicle. And I will see if the target acceleration that I have calculated here is more than the current acceleration of my ego. If so, then I'll put a throttle of 20%. So that means these are some hard-coded values. These are without any filters to the actuator. So these are just to give you an example how it works. So I'll have a 20% of throttle here so that my ego acceleration reaches to the target acceleration. Yeah. If the target acceleration is less than ego acceleration, then what I would do is I will remove any throttle request that I am putting. Instead of that, I'll put a brake so that this condition means my ego is moving at a higher acceleration rate than it should be, and it might collide. So I will brake automatically. At a particular situation when the target acceleration and ego acceleration is same, which will vary for a very fraction of second, then I'm just putting a throttle of 10%. So with this control model, let's take a use case. So this is a use case. So whatever I have written there, I have put it into a simulation environment, keeping all the vehicle dynamics into picture. And there I have created a situation where the traffic ahead of me drives at a constant speed of 10 kph, and then it slowly gradually increases its speed to 20 kph and then 30 kph, and then comes to complete halt. So with that situation, with that use case in mind, let's see how this ego vehicle is performing with the control model mounted in it. So you see here the speed is constantly increasing because the object is still not detected, and here the throttle position is 20% constantly kept. So that is why the speed will be increasing constantly. Somewhere here the object got detected. So you see here the speed at which it got detected was 43. So at this particular time the traffic is driving at a speed of 10 kph. So my ego should adapt to the 10 kph speed. So you see here, it is constantly keeping a 10 kph speed. So now now this traffic is accelerating to 20 kph speed. So I also adapted my ego. This is a basic cruise control function. So in the actual vehicle, they does it with by putting the powertrain request and the brake torque request. But I am doing in order to simplify it for you, I'm putting it to through the gas pedal and the brake pedal. So now this guy, the traffic accelerates to 30 kph. I also adapted to 30 kph, and then he will come to complete halt. So my ego also has to come down to from 30 to 0, keeping the 2.5 second in mind. So this guy stopped, and my ego also completely stopped. Autonomous driving, whatever I have prepared for today, the autonomous driving levels and also some examples of the control models that is the present in modern day cars, and also I just showed you one control model that takes care of adaptation of the traffic speed.